This lesson goes over the difference between exothermic reactions and endothermic reactions. Exothermic reactions. Let's see if we can figure out, by pulling apart that word, what exothermic means. Think about other words that have the prefix X. Exoskeleton is a skeleton that's on the outside. Expel means to be pushed out or kicked out. Explosion is a reaction where heat and stuff blow out from the center. So this X or exo prefix seems to imply things coming out or moving out. Therm, the stem therm, let's think of other words that have that therm in it. A thermometer is a device for measuring heat. A thermostat, that's that thing that you set in your house to change what temperature the heat comes on at. It controls the heater. So X seems to mean pushing out or kicking out, and therm has to do with heat. So exothermic reactions, then, are reactions that give off heat. They push heat out from the reaction into the surroundings. An example is wax burning. That pushes heat out into the surroundings. If you put your hand near that flame, you would feel the heat coming off of that reaction. Sometimes exothermic reactions can be quite violent, like an explosion. Sometimes exothermic reactions aren't visibly glowing, but they can give off heat. For example, when it's very cold out, you can put down a special kind of salt. It's calcium chloride. And it actually reacts with the water and creates a bit of heat, and it can help melt the ice down to a lower temperature than regular sodium chloride salt can. If you touch an exothermic reaction, it'll feel hot, and that's because it's giving off heat. That heat that it's giving off would come into your hand. Those of you who happen to be Twilight fans, you can think of the werewolves as being exothermic. We can look at chemical equations and we can see what it looks like when a reaction is exothermic. So here's a reaction that shows the burning of methane. CH4 is methane, it's a fossil fuel, and it'll react in the presence of oxygen. You need oxygen in order to have a fire. So methane will burn or combust with oxygen. When that happens, it yields two different types of molecules, carbon dioxide and water. Remember, burning of fossil fuels produces carbon dioxide into the atmosphere. We see that part of the chemical equation. But it also gives off heat. We haven't typically shown heat in our chemical equations because when we went to balance these equations, all we were looking at was the atoms themselves. But in this case, heat is also one of the products of this reaction. And this is why when we burn methane, things get hot. Now let's look at endothermic reactions. And again, let's look at that prefix endo. We have an endoskeleton, which is a skeleton that's on the inside. If you enter a room, you're coming in. So that endo seems to mean coming in or bringing in. So endothermic reactions take heat in from the surroundings. An example might be a cold pack. So you can see here that the directions on this cold pack say to squish it and then shake it, and then it will get colder. What that cold pack is doing when you squish it and shake it is you're initiating a chemical reaction inside there that takes heat away from whatever it's in contact with. So if that cold pack is touching something, say it's touching your swollen knee that you just injured, it's going to take heat out of your knee, and your knee is going to feel colder. Endothermic reactions feel cold to the touch. Again, going with our Twilight analogy, the vampires would be endothermic. Some chemical changes are endothermic. So for example, if we take calcium carbonate, that's limestone or chalk, and we heat it up. So we take the calcium carbonate plus heat. That heat gets absorbed, and the calcium carbonate gets broken down into calcium oxide and carbon dioxide. This chemical change sucks heat out of the surroundings and uses that heat to break apart a molecule. Not only are chemical changes going to be endothermic, but there are a number of physical changes that are going to be endothermic as well. For example, in that cold pack, what was happening was we were dissolving something. We're dissolving a chemical called ammonium chloride in water. So we start off with solid ammonium chloride. It's sort of a flaky white powder there. And we add it to water. And what happens then is it's going to suck some heat out of the surrounding environments. That's the reason that cold packs work, is they suck the heat out of what's nearby. And the combination of that heat, the liquid and the solid, dissolves the ammonium chloride. So it dissolves it into ammonium ions and chlorine ions. Again, this is a physical change. Dissolving isn't a chemical change, but it is a change that is endothermic. Another common endothermic change is melting ice. If you think about it, you start off with water that's a solid, and you end up with water that's a liquid. So the chemical equation, or the equation that shows this change, it's a physical change, so it's not a chemical equation, but it shows the change from a solid to a liquid. In order for that to happen, to change a solid to a liquid, you need to add heat. Where does the heat come from? Well, the heat comes from your hand. As heat comes out of your hand feels colder. Endothermic reactions feel cold to the touch. Who cares? Like, why do we need to know about this stuff? Well, chemists would use their knowledge of endo and exothermic reactions to do things like, for example, decide what ingredients they want to use in those hot and cold packs. They're going to be looking for ingredients that are safe in case the pack gets ripped, that produce enough cold that it cools down an injury but doesn't give you frostbite, or enough heat that it warms up your hands but doesn't burn through your pockets. They might use it, for example, in ski slopes where they artificially make and blow snow so that so you can ski even when it hasn't snowed recently. They'll add chemicals to the water in that snowmaking equipment to help it stay colder even when natural plain old water would melt. They also want to make sure that things don't accidentally blow up. Chemists know, for example, that if you take sodium and place it in water, you get a highly exothermic reaction. And so we don't see people shipping chunks of sodium around willy-nilly, because if they happen to get wet, it would be really bad.